let's consider some examples of application of the second order conditions. So we have the following problem. So we want to minimize x1 plus x2 subject to x1 squared plus x2 squared minus 2 is less than or equal to 0. So minimize x1 plus x2 subject to x1 squared plus x2 squared minus 2 is less than or equal to 0. And geometrically, the feasible region is given by a disk of radius of square root of 2 centered at the origin. So this is our feasible region. We want to minimize x1 plus x2. So the isocost line would be like this, passes through the origin. So x1 plus x2 is equal to 0, right? But if we decrease the value for x1 plus x2, then we move this line on parallel down. And then we'll see that the last point that we will touch as we exit the feasible region will be somewhere here. And in fact, we can see that this point would be -1, -1. Now let's apply the optimality conditions to this problem. So first we'll write down the Lagrangian. So we have Lx. So in this case we don't have the equality constraints. We just have Lx mu. So it's given by x1 plus x2, and then plus mu multiplied by x1 squared plus x2 squared minus 2. So this is our Lagrangian, right? And then we formulate the Kkt conditions. So we'll have the first order derivative with respect to x1 will give us 1 plus 2 times mu times x1 is 0. The first order derivative with respect to x2 will give us 1 plus 2 mu times x2 is 0. Then we have the complementary slackness. Mu times x1 squared plus x2 squared minus 2 is 0. Finally, we have the inequality constraint, which is x1 squared plus x2 squared minus 2 is less than or equal to 0. And we have mu greater than or equal to 0. So these are the conditions that we have. We need to solve this system now, right? So we typically start by looking at the complementary slackness conditions. So first, if we assume that mu is equal to 0, then we have 1 is equal to 0 from the first and second equation. So mu cannot be equal to 0, right? So we don't have stationary points inside of this circle, obviously. Now, the second case we need to consider is mu is not equal to 0, which means that x1 squared plus x2 squared minus 2 is 0. Now we can express x1 and x2 through mu from the first and the second equation, right? From the first equation we'll have x1 is given by -1 over 2 mu. From the second equation, x2 is given by 1 minus 1 over 2 mu. And then when we plug in these expressions for x1 and x2 in this equation here, then we'll have 1 over 4 mu squared plus 1 over 4 mu squared is equal to 2, which is the same as 4 mu squared is 1. So from here we get mu is plus minus 1/2, but because mu must be greater than or equal to 0, we have mu is equal to 1/2. Now we can plug in this value of mu here to compute x1 and x2. We'll have x1 is equal to -1, and then x2 is also equal to -1. All right, so the only stationary point that we get is -1, -1, and the value of mu is given by 1/2. Okay, so now we can apply the second order conditions. For the second order conditions, we need to compute the Hessian of the Lagrangian, right? So the Hessian of the Lagrangian, so we look at the second order derivative with respect to x1 twice first. This will give us 2 mu. So then x1, x2, 0, 0 here. and then the second order derivative with respect to x2 twice will give us 2 times mu as well. So this is our Hessian of the Lagrangian. So and for our point x star, so this is our x star, and we'll have just the identity matrix here. Obviously, in this case, the Hessian of the Lagrangian is positive definite, so and we have y transpose times the Hessian of the Lagrangian times y is actually greater than 0 for any y which is not equal to 0, including all y's that belong to t of x star mu. Therefore, we can conclude that the second order sufficient condition is satisfied, and this point is a strict local minimizer. In fact, we can observe that this problem is convex, right? So we have a linear objective, and then we have a convex feasible region. We know that for a convex problem, the Kkt point will actually be the global minimizer. Because of that, the point is a global minimizer here, and we can also see geometrically, of course, that this was the solution that we obtained. Now let's consider a non-convex example where we are minimizing a non-convex function over the exterior of a unit circle, which is also a non-convex set, right? So we have the problem of minimizing minus 0.1 times x1 minus 4 squared plus x2 squared, subject to x1 squared plus x2 squared is greater or equal to 1. And obviously we can see that the objective is not bounded below in the feasible region. Let's say if we take x2 is equal to 0, and then take x1 tending to plus infinity, then the objective will tend to minus infinity, and we will stay within the feasible region because this is the outside of the unit circle. Obviously, there is no global minimizer here. For the gradient of the Lagrangian, we have this vector here. Then for the Hessian of the Lagrangian, we have this matrix, right? We can apply the optimality conditions now. So first, we'll look at the Kkt conditions. If we write down the Kkt conditions, we can see that there will be x star is given by the vector 1, 0 transposed, and mu star is 0.3. Our only constraint will be active in this case, right? So I of x star is equal to 1. That's the index of the first constraint, right? And then to check the second order conditions, we look at the tangent space. And the tangent space is given by the gradient of g1 of x star. So we only have one constraint again, right? So the Jacobian is given by the gradient of g1 of x star. So, and to compute the tangent space, we need to find the set of y's such that minus 2 times y1 plus 0 times y2 is 0, right? So, and obviously this is the case for the vectors where the first component is 0 and the second component is any real number, right? And now if we consider the product of y transposed times the Hessian of the Lagrangian times y, where y belongs to t of x star mu, we obtain 1.4 y2 squared, which is greater than 0 whenever y is not 0. And by the second order sufficient condition, we conclude that this point x star that we computed is a strict local minimizer for our problem.
It's go time!
Let's consider one more example that involves both equality and inequality constraints. So we look at the problem of minimizing x2 minus x1 subject to the equality constraint x1 squared plus x2 squared is equal to 4, and then x1 plus 1 squared plus x2 squared is less than or equal to 4. All right, so what this problem is geometrically is the following. So we have the first constraint defines the circle of radius 2 centered at the origin, right? The set of points satisfying the first constraint, right? And now the second constraint defines actually a region that is given by the disk, the circle of radius 2 also, but we have the inequality constraint in this case, so the interior of the circle is also a part of the feasible region. So in this case, the circle is actually centered at the point -1, 0. Okay, so this will be the center of this circle, and the radius will be 2. So overall, the feasible region will be just given by this curve here. Okay, so which is a part of the first circle. All right. Now our isocost line in this case is given by x1 is equal to x2, so this is the isocost line corresponding to the cost of 0. If we want to decrease it, this line will go this way. So if we apply the Kkt conditions for this problem, then we'll find the following 3 points. The first point will be x1 is given by minus square root of 2, with lambda 1 given by minus 1 over 2 square root of 2, and then mu 1 is 0. This point will actually be somewhere here. So this is minus square root of 2, So this is our point x1. The second Kkt point, x2, is given by minus 1/2 for x1, and then square root of 15 over 2 for x2. Okay, so the corresponding lambda multiplier will be minus 1/2, 1 plus 1 over square root of 15. And then the corresponding mu will be 1/2, 1 minus 1 over square root of 15. Finally, the third Kkt point will be x3 given by minus 1/2 for x1, and then minus square root of 15 over 2 for x2, with the corresponding value of lambda given by minus 1/2, 1 minus 1 over square root of 15, and then mu 3 is given by 1/2, 1 plus 1 over square root of 15. Okay, so we got these 3 points, and then the Hessian of the Lagrangian is given by 2 times lambda plus mu, then 0, 0, and 2 times lambda plus mu. Okay. If we look at the first Kkt point, we can see that the Hessian of the Lagrangian for x1, lambda 1, and then mu 1 will be given by minus 1 over square root of 2, 0, 0 minus 1 over square root of 2. Okay, so this is a negative definite matrix. Therefore, we don't even need to compute the tangent space here, because this is a negative definite matrix, so the inequality y transpose times the Hessian of the Lagrangian times y less than 0 holds for any non-zero y, including for those y's that are in the tangent space, right? Therefore, we can conclude that x1 is a strict local maximizer. So it should be noted here that the point x1 is interior with respect to the inequality constraint, right? Therefore, in this case, the inequality constraint doesn't really matter. The local optimality of this point is the same as if we were just considering the problem with one equality constraint here. And we can see that actually, yes, indeed, this is a point of a strict local maximum. So if we are moving the isocost line in that direction, then this will be the last point that we touch in the feasible region. So in fact, geometrically, we can see that this point is a global maximizer for our problem. So now the other 2 points, and by the way, these 2 points on this illustration would be this point right here. Of course, the illustration is not perfect. The x1 coordinate should be the same for both points, right? So, but these are the 2 points, so these are essentially the end points of this curve here. for these 2 points, geometrically, we can see that actually one of them is a strict local minimizer, the other one is also a strict local minimizer, and in fact, this point would be the global minimizer, right? If we want to apply the second order conditions to show this, we need to actually compute the tangent spaces, all right? So for the tangent space of the second point, T of x2, in fact, it coincides in this case with T of x2 mu, because the Kkt multiplier mu is not 0. All right, so this will be the set of points y such that the gradient of h in x2 transpose times y is 0, and then the gradient of g of x2 transpose times y is 0. So, and then if you write down this system, so it will be minus y1 plus square root of 15 y2 is 0. y1 plus square root of 15 y2 is 0. And we will see that the only point that belongs to this tangent space is the point 0, 0. And in cases like this, the second order sufficient condition is automatically satisfied because it tells us that for all points from this set T of x2 mu, we must have the inequality strictly satisfied, but since there are no points other than 0, the second order sufficient condition actually holds, right? Indeed, for all non-zero points from T of x2 mu, which there are none, that inequality holds, right? So therefore, the second order sufficient condition is satisfied, and we see that x2 is a strict local minimum. For the third point, we can also show that T of x3 mu just consists of one element, the point 0, and therefore we can also conclude that x3 is also a strict local minimizer. Therefore, we found that one of the 3 points was a strict local maximizer and the other 2 were strict local minimizers. And also considering that the feasible region of this problem is a compact set, we can conclude that this point here, which is x3, so and this point is x2, so we can conclude that because among these 3 points, the smallest value of the objective corresponds to x3, this is our global minimizer. All right, so x2 is a strict local minimizer, and then x1 is actually a global maximizer.
Wow.